So, we will continue with the proof of the characterization of the continuous linear functionals on LP of mu. So, recall that P is between 1 and infinity, 1 is included, but infinity is not included. The measure mu is assumed to be sigma finite. Okay. So, let us start. So, uniqueness we have already proved. So, assume that measure of the total space is finite, mu is a finite positive measure. Okay. So, for measurable sets E, define lambda of E to be T of chi E. Okay. So, recall that T is a continuous linear functional from LP of mu, and we are trying to find a G which defines T, right. So, this is continuous and linear. So, chi E is a function, chi is a measurable function, and it is in LP of mu because mu of E is finite, right. So, remember mu of the total space is finite. Okay. So, chi E will be in LP, there is no problem. So, this makes sense. Okay. So, this is well defined. This is well defined. Now, if E1, E2, etc., E capital N are disjoint, suppose they are disjoint measurable sets of course, then the characteristic function or indicator of Ej union Ej j equal to 1 to n, because they are disjoint they become a sum j equal to 1 to n chi Ej. Okay. So, these are all functions in LP. So, I can apply T to it. So, if I look at lambda of union Ej j equal to 1 to n, okay, this is by definition T of indicator function of union Ej j equal to 1 to n, finite union. Because of the linearity of T and chi of union j equal to 1 to n being the sum, this is same as summation j equal to 1 to n T of chi Ej, but T of chi Ej is lambda of Ej, right. So, this is summation j equal to 1 to n lambda Ej. So, if I take finitely many disjoint sets, lambda of the union is the sum of the lambda Ej's. So, that is finite additivity. I want to say it is countably additive, and so it is a complex measure. Okay. So, let's try to prove that. Okay. So, to prove countable additivity. Okay. So, to prove countable additivity, let write E as union Ej j equal to 1 to infinity, right, Ej disjoint, and I want to say lambda of E is the sum of lambda Ej's, right. That is what countable additivity means. Okay. So, then chi of union j equal to 1 to n capital N Ej, well, I want to say this converges to chi of union Ej j equal to 1 to infinity now as capital N goes to infinity. Where does it converge? In LP of mu. Okay. Well, how do I? So, recall that we are assuming. So, we are assuming P is strictly less than infinity. Okay. Otherwise, this is not true. Okay. So, P is strictly less than infinity. So, how do we do this? So, we look at the integral over x, the difference between these two, right. So, chi of j equal to 1 to n Ej minus chi of union j equal to 1 to infinity Ej modulus to the P d mu, right, and to the 1 by P, that is the LP norm. I want to say this goes to 0. Okay. So, well, what is this? This is simply, remember Ej's are disjoint, right. So, let's draw some picture. So, this is E is the union of Ej's, right, like this. So, I have E1, I have E1 here, I have E2 here, E3 here, and so on, right, E4 here and so on. So from the union, if I subtract the first n ones, right, so I am looking at chi of A minus chi of B, where B is contained in A, right. So let's do that, that will be much more clear then. So if I have some set A and let us say I have a set B, what is chi A minus chi B? So that is just chi of A minus B, right, it is the complement. So here I will get the whole union minus the first n elements, n components, which is just the union of the remaining, right. So j equal to n plus 1 to infinity Ej, right, modulus of P d mu, okay, which is mu of union j equal to n plus 1 to infinity Ej, right. So if I want, I can take this to the 1 by P, okay, but because that is the LP norm. So this to the 1 by P LP norm. So I have 1 by P here, and this will of course go to 0 as capital N go to infinity, right, because I'm getting a decreasing sequence of sets, right. So this is a decreasing sequence of set, a decreasing sequence of sets, and mu is a finite measure. So there is no problem in applying the theorem. So that goes to 0. So which means that it converges to chi E in LP mu. So T of that will converge to the corresponding union, right. So T of chi union j equal to 1 to n Ej will converge to T of chi E, right. E is, remember, E is the infinite union, Ej, j equal to 1 to. But this is simply the sum, right. This is, remember, this is just lambda of E. This is the sum of T of chi Ej, j equal to, because simply the linearity, and as n goes to infinity, this goes to the sum, right. So this is summation j equal to 1 to infinity lambda of Ej. So that tells me that lambda is a complex measure. So all this simply implies that lambda is a complex measure. Okay. All right. So let me recall what we did. We simply had a continuous linear functional. Since the proof is wrong, I'll just recall what we did so far. I had a continuous linear functional. Okay. We defined lambda of E to be T of chi E. This we did for every E in script f. So that is a set, that's a set valued, that's a complex valued map on script f, and we just proved that it's a complex measure, right. Then continuity of T implies lambda is a complex measure. Lambda is a complex measure. Okay. Now if mu of E equal to 0, so remember mu is our sigma finite positive measure, right. So I have x, f and mu. Mu is the fixed sigma finite measure, sigma finite positive measure. If mu of E is equal to 0, what can you say about chi E as a measurable function? So this will be 0 almost everywhere mu, right, because the measure set has measure 0. So T of chi E will be 0 because it's the element 0 in LP, right. It is in the same equivalence class of 0. So this is 0, but that is T of chi E is the definition of lambda E, right. So lambda of E is 0. So if mu of E is 0, lambda of E equal to 0, which is same as saying lambda is absolutely continuous with respect to mu. Okay. So remember mu is, well, we assumed mu to be finite to start with, right. So not even sigma finite, it's finite. Okay. So now we are in good shape. So you know what to do when you see one measure absolutely continuous with respect to the other measure. Well, what do? Apply Radon-Nikodym theorem. So by Radon-Nikodym theorem, we have a Radon-Nikodym derivative, right. So we have a unique G, so that is instead of H I am using G in L1 of the positive measure mu such that T of lambda of E such that lambda of E equal to integral over E G d mu, correct. So this is what the Radon-Nikodym theorem tells you. The Radon-Nikodym derivative is the function G. Okay, so we have a unique G in L1. Okay, so that is something which you should keep in mind. G is right now in L1. Okay, mu is finite, so L1 is LP is contained in L1. Okay, so we have to still further reduce the space where G belongs to. So we will see that. So let's write this in a different form. So this tells me that T of chi E, this is lambda of E of course, equal to integral over E G d mu equal to integral over X chi E G d mu. Okay, so now comes slightly tricky arguments. One has to be very careful about what space we are looking at and things like that. So we have G, as of now we have G only in L1 and we also have mu x is finite by assumption. Okay. Now T is linear, here also it's linear, right, it's an integral. So instead of chi E I can take a symbol function, right. So by linearity we'll have T of S, okay, equal to integral over X S G d mu for every simple function, right, for every simple function S in LP of mu. Well, it does not matter because we have a finite measure space. So any simple function will be in any LP you want, right. So for every simple function S. Okay. Okay, so let's box that as well. So now we want to go to functions. Okay, so how do we go to functions? Well, from Ts, so if I take f to be bounded, so let's take f to be in L infinity of mu. Okay, so that is why I said spaces should be kept in mind. The function g is in L1. Okay, so I don't want to put any arbitrary f here. I want to put only f in L infinity so that by Holder's inequality it is finite. Okay, so for f in L infinity I have simple functions Sn converging to f uniformly. So recall this was one of the first theorems we proved. If f is positive we have positive simple functions converging increasing to f, but if f was bounded the convergence was uniform, right. So if f is in L infinity, which means f is essentially bounded except on a set of measure 0 which you can discard, you will have uniform convergence. Okay, so if Sn converges uniformly, that is same as saying Sn minus f, the L infinity norm goes to 0. So it will converge in any LP you want because the measure is finite. So let me write down that integral over mod x Sn minus f, the LP norm. Okay, so this I replace by the L infinity norm. So integral over x Sn minus the L infinity norm to the p d mu to the 1 by p, but L infinity norm is a constant, so that comes out to the p is there and to the 1 by p is there, so that is less than or equal to, so what remains is mu of x, right. So mu of x to the 1 by p L infinity norm of S1 Sn minus f, which goes to 0. So I will have convergence in LP. Okay, so Sn converges to f uniformly, which is same as saying the L infinity norm of Sn f minus f goes to 0 implies Sn converges to f in LP. Okay, so that is because of measure being finite. Okay, that is very crucial. So now you apply whatever you want here, because Tsn I know that this is equal to integral over x Sn g d mu. Okay. What happens to the left hand side? Well, this will converge to, because Sn converges to f in Lp and t is continuous, you will get this converges to Tf, right, in the complex plane. Well, I want to say what happens to this. Sn converges to f uniformly and g is in L1. So, let us see Sn times g converges to f times g almost everywhere, and mod Sn mod g is less than or equal to some constant times mod g, which is in L1. Why does it why do I have a constant? Because f is bounded and Sn converges to f uniformly. So, all the Sn's are bounded by some fixed constant, right. So, maybe 2 times the L infinity norm of f, for example. So, this sequence of functions is bounded by a function which is in L1. So, I can apply dct, right. It will converge to the corresponding limiting integral. So, that is f times g d mu. But these two are equal. So, these two will have to be equal. Okay. So, what did we do? We went from simple functions to bounded functions. So, let us box that. Okay. So, now we have gone one step ahead. Tf equal to integral over x f g d mu for every f in L infinity of mu. Okay. So, we have gone up to that. So, we have got a g and we have got a representation for t, but only for functions in f. So, we need to extend. So, there are two things to do. One, need to extend this to all f in Lp, and we also need to prove that g is in Lq. So, okay, so there are two things to do, right. G as of now is only in L1, right. G as of now only in L1. Okay. Lq is strictly contained in L1 because mu has finite measure. So, there are two things to do. Okay. So, here we split the cases. Okay. So, case 1, let us take p equal to 1. So, if I take p equal to 1, q is infinity, right. So, what we have is, so let's write this here so that we can see this again. Tf is integral over x f g d mu for every f in L infinity mu. Okay. The extra information is that we know that g is in L1. Okay. G is in L1 of mu. That is all we know. Okay. So, let's box this, and this will be used again. So, assume p equal to 1 and q equal to infinity. Okay. Call this star. So, from star we have t of chi e. Well, again take chi e because chi e is bounded. Okay. So, I am instead of f I am putting chi e. This is equal to integral over e g d mu. Okay. So, now, well, you know what is going to happen. You want to show that g is in L infinity, right. So, here, so we need to show that g is in Lq. So, show that g is in L infinity, right. Q is infinity here. So, we need to look at averages of g and see where it is, right. So, look at integral over e g d mu modulus. So, this is equal to modulus of t chi e, which is less than or equal to, remember whenever you have Tf, t is continuous. So, I have norm t, which is a finite quantity, that is the supremum of Tf mod Tf over the unit ball times mu of e, right. Well, why mu of e? So, t here is a continuous linear functional from L1 mu to c, right. P is 1, right. So, I am looking at L1, and so if I look at Tf modulus of Tf will be less than equal to norm T times norm of F, which is the L1 norm. Okay. So mu E here is the L1 norm of chi E. Correct. So we just use that. Alright. Which is same as, so this tells me that the averages of G, right, if mu is positive, you look at averages of G, this is less than or equal to norm T. Okay. Hence norm T is finite because T is a continuous linear functional. So norm T is a finite quantity, hence G will be bounded, right. G is in L infinity of mu, and the L infinity norm of G is less than or equal to norm T. Okay. So remember, initially G, the extra information was that G is in L1. Now we have proved that G is in L infinity. Okay, so let us do that in the second case as well. So case 2, 1 less than P, strictly less than infinity. Okay. So here, so write alpha times G equal to mod G. Alpha is a measurable function with mod alpha equal to 1, right. So this is just alpha. What is alpha? Alpha is mod G by G when G is not, we have done this before, 0 otherwise, if you like, or 1 otherwise, so that mod alpha is 1. Okay. Alright, so we have a measurable function alpha which does this job. Now we do exactly what we did earlier, but we don't know about bounds of G. So we bring in bounds for G. So En, you look at this set X such that mod Gx is less than or equal to n. Okay, so that G is bounded, right. So G is bounded on En by n. Okay. Define. So if you look at the proof earlier, we looked at some function like this, right, to exactly get the equality of the norm T and something else. So we are going to do that same, except that we have no bounds on G right now. So we make G bounded by taking the set where G is less than or equal to n. Okay, and define F to be chi En, so that everything is restricted now to mod G less than or equal to n times mod G to the q minus 1 into alpha. Alpha is that set, right. So that this is precisely what we did earlier. Okay, except the En part. So the En part will make sure that G is bounded. Okay. So this is of course in LP because it's bounded. Okay, because the function is bounded, f is bounded, and mu of x is finite, right. So it will be in all LP. So in particular in the LP we want. Now use star again. By star, so star tells me that T of f is the integral, right. So T of f would be integral over x f g d mu as long as f is bounded, right. Okay, so what is this? This is equal to fg. F is indicator chi n is there, so I will be integrating over n. Then I have mod g to the q minus 1 and times alpha, right, and G. So what is alpha times G? Alpha times G is mod G, right. That is how we have defined alpha. So I have mod G to the q minus 1 here and I have a mod G here. So that will give me mod G to the q. So this is only to bring in mod G to the q. Okay. So integral over En mod G to the q d mu is equal to T of f. Okay, so I'll take the modulus because it's positive. This is less than or equal to Tf, I know, is norm T times LP norm of f, right, because T is a continuous linear map on LP. Okay. Now what is this? This is integral over x mod f to the p d mu to the 1 by p. Okay. But f is given by something like this. So this is integral over En mod f to the p. Alpha has modulus 1. I have mod g to the p into q minus 1. So mod g to the p into q minus 1 d mu to the 1 by p. Okay. P into q minus 1 is q. We have seen this before. So, this is integral over En mod g to the q d mu to the 1 by p, and this is finite of course. This is finite because on En g is less than or equal to n, right, and mu En, and mu has finite measure for every set. So, this is a finite quantity. So, let me write this as, so let me write one more line to make it very clear. So, what we have proved is integral over En. Recall that we are trying to prove that g is in LQ, right. So, d mu, this is less than or equal to norm t times integral over En mod g to the q d mu to the 1 by p. Okay. Now, this is the same quantity, right. So, you have one quantity here and you have the same quantity to the 1 by p. So, you can take it to the other side because it is finite. So, this implies if I take it to the other side, I will have integral over En mod g to the q d mu to the 1 minus 1 by p. 1 minus 1 by p is 1 by q, right, because 1 minus 1 by p equal to 1 by q. So, use that to put it here. Is less than or equal to norm t. Now, this is independent of, so independent of n, right, independent of En. Okay. So, I can let n go to infinity and that will give me the whole space, right. So, okay. So, let us recall that En was the set where mod g was less than or equal to n, right. So, En's will increase to union En, which is the whole space, right, because g is bounded, we know that. So, this tells me that if I let n go to infinity, we are going to get integral over x mod g to the q d mu to the 1 by p is less than 1 by q is less than or equal to norm t. Okay. So, that is same as saying g is in LQ, which is what we wanted to prove, right. So, in both cases, case 1 and 2, what we proved was the g we got here, okay, makes sense. Well, g we got here is actually in LQ, where q is the conjugate exponent. Okay. So, let us recall star once more and then we can complete the proof. So, recall star again, call star, what is that, t of f equal to integral over x f g d mu for every f in LP, sorry, L infinity of mu. Okay. So, recall, remember that is only for L infinity, but now we know that, g belongs to LQ. Okay. Initially g was only in L1. Okay, remember mu is a finite measure, so L1 is a bigger space. So, both of this, both sides, so RHS would be a linear, continuous linear functional on LP. Why? Because G is in LQ, right, because G is in LQ. Whenever you have a LQ function, it defines a linear function on LP. LHS is also a continuous linear functional on LP, that is by assumption, right, we started with that, and they are equal on L infinity, right, but L infinity is dense. Okay. So, that is what you need to see. I have two linear functionals, TF and this right hand side, they agree. So, two linear functionals, two continuous linear functionals on LP of mu agree on L infinity of mu, which is contained in LP of mu, because mu is finite, right. So, mu of x is finite, that is the reason this is true, and of course, this is dense, right, because I have all simple functions here and simple functions are dense. So, I have two continuous functions agreeing on a dense subset, so they will have to agree everywhere. Okay. So, hence these two linear functionals agree everywhere, that means on LP of mu, which is same as saying, so write it in box. So, T of f will be now equal to integral over x f g d mu. Now it will agree. So from L infinity we are able to go to LP by denseness. So for every f in LP of mu, which is what we wanted to prove, correct. So we have proved the case. So this proves the case when mu of x is finite. Okay. So we have to assume that mu x is infinite, and then we will use this particular case and then do it. Okay. So let us take few more minutes to do that. Okay. So next, assume that mu x is infinity, okay, but mu is sigma finite. Remember that mu is sigma finite. Okay. So then, since mu is sigma finite, we have a w, right, such that 0 less than to w less than 1 and w is in L1. Okay. So let's define a new measure. So I want to define a finite measure. Define d mu tilde equal to w d mu. Okay. So then mu tilde is a finite measure, right. So mu tilde of x equal to integral over x w d mu is finite. So finite measure. So previous results apply to, so previous proof applies to mu tilde, correct. Okay. So if I have a continuous linear functional on LP of mu tilde, I can apply the theorem. So how do I get that? So first look at the map. So consider the map. Capital F going to w to the 1 by p capital F. Where does it go from? So it is mapped from LP of mu tilde. So remember, mu tilde is this measure, to LP of mu. Mu is the infinite sigma finite measure. Okay. Well, is this, what kind of a map is this? So let us see if it is landing in the space right hand side. So in the right hand side, so you look at this map. So I'm looking at the range, right. So w to the 1 by p f. I want to know if it is in LP. So I take the LP norm with respect to the measure d mu. What is this? This is integral over x mod f to the p. I have w d mu, right. Remember, w is positive, but f comes from this measure, right. This measure is here. So this is finite. So this is the LP norm of, so I can take a 1 by p if you want. So this is the LP norm with respect to mu tilde, right, to the p. So that means this is an so if I look at the LP tilde norm of LP mu tilde norm of f, that is same as the LP norm of w to the 1 by p f, right. Okay. So I'm writing a trivial thing in symbols so that it's clear. So that means the map f going to w to the 1 by p f preserves the norm, so that preserves the distance, and so it's an isometry. Okay. So hence this is an isometry. Isometry meaning df, the distance between f and g will be same as the distance between the images. So that once you have this, that immediately follows. And of course you can retrace it by multiplying by w to the 1 minus p, right. So it is actually an onto map. Okay. So it's an onto. So these two spaces are identified by this map. That is what we have. So it's a linear isometry. All right. So now if I look at LP of mu tilde, okay, I have of course this map LP of mu. What is the map? Capital F going to w to the 1 by p f. Okay, and here I have the map T, which is the continuous linear map, right. So if I compose, I get a map T tilde. So let's call that T tilde, which is continuous and linear, right. So what is T tilde? So T tilde of f is T of w to the 1 by p capital F. Then T tilde from LP mu tilde to the complex plane, right, is continuous and linear. Okay. But remember, mu tilde is a finite measure. So, previous result applies. Okay. So, few more lines. Previous result says there exists some G unique, right, in LQ of mu tilde. Remember, Q is the conjugate exponent, and I have a continuous linear function on LP mu tilde now, okay, such that T tilde of f is equal to integral over x f g d mu tilde, right. So, everything is applied to mu tilde because it is a finite measure. This I can write as integral over x f g w d mu, right. Mu tilde is just d mu tilde is equal to w d mu, right. That is the definition of mu tilde. Okay. But this is true for every f in LP of mu tilde. Okay. So, if f is in LP mu tilde, I multiply by w to the 1 by p, I will go to LP mu. So, let us do that. Okay. So, T of w to the 1 by p f, okay, because this would be in LP mu, correct. This by definition is of course, because of the T tilde definition, I will have integral over x w to the 1 by p f into w to the 1 by q g d mu. Okay. So, this I am writing as w, I am writing as w to the 1 by p into w to the 1 by q, right, because 1 by p plus 1 by q is equal to 1. So, I call this small f and I call this small g, then I have T of f equal to integral over x f g d mu, okay, where g equal to w to the 1 by q capital G, and that is in LQ of mu. Well, what is the LQ part? Because if I take mod g to the q integral over x d mu, this is same as integral over x w mod g to the q d mu, right. So, that is integral over x mod g to the q d mu tilde, right. D mu tilde is w d mu, which is finite, right, because g comes from LQ mu tilde. So, that is all we need, right. So, we have a function small g which is in LQ mu, which defines my linear functional T, and of course, that is for every f in LP. Yeah, all right. So, we will stop here. So, we will stop here. What we have just finished is the characterization of continuous linear functionals on LP of mu, where mu is a positive sigma finite measure and p is between 1 and infinity. 1 is included, but infinity is not included. The same result holds if mu is not sigma finite, but p is strictly between 1 and infinity. Okay. So, essentially the same proof with appropriate modifications will work, and it is very important that p has to be strictly greater than 1. For p equal to 1, mu is sigma finite is necessary for this result to be true. So, for the case when mu is non-sigma finite, I refer you to Follen's book on real analysis. You will see the proof for p strictly between 1 and infinity when mu is not sigma finite. Okay. So, we will stop here.